please.
Hi, I'm Kent Charrington.
This is Dallin Thewison.
And Logan Waite.
And today we're going to go over these problems with y'all. We're going to go over question number 1 first. I'll just read through it. So it says, Priscilla Lane and Margaret Green studied the relationship between 3 linked genes affecting coat color in mice. The 3 recessive genes are mahogany, gouty, and ragged. The wild-type versions of these 3 genes are dominant. So then they carried out this test cross, and these are the results. And then, so for question 1, part A, it says, determine the allele arrangement in the heterozygous parent. So to do this, we would look at the outcome, and we would find the 2 biggest results, okay, which we find to be 76 and 69. And we take those phenotypes next to them and put them next to each other, and that's pretty much how we find the parent genotype. Then for part B, we determine the gene order of these 3 linked genes. And to do that, as it kind of shows in the picture there, we take the 2 smallest ones, which are the 1 and 1, and take those phenotypes next to each other. But then we try and figure out which one needs to be switched so that it matches what the parent one looks like. And we find that it's the one box there. So we find the gene order to be RG, and then the A, and then the MG in that fashion, okay? So that's how we did part B. In part C, we constructed a linkage map showing the map distances between the 3 genes by doing the map as shown in part C there. So we add together the 1 plus 1 plus the 12 and 13, divide it by the total number of offspring, and multiply it by 100 to get 13.11 mu. That's the distance between the A and MG phenotypes. And then we did the same thing for the 16 and 18, which would give us the distance between the RG and A phenotypes. Okay, so that would give us the map sequence. Okay, and then for part D, to calculate the interference, we took 13 and 17, divided by 100, multiply them together, and then we took that, multiply it by the total 206 to get 4.72, and then we plugged that into the interference equation, which is 1 minus 2 divided by 4.72, which would give us 0.57 or 57%, and that would be our interference value there.
Okay, for question 2, we're going back to the fruit flies again, and it asked us for the gene arrangement of these 3 linked genes. And so, like Kent explained, to get that you've got to locate the 2 greatest categories of offspring, which is going to be 314 and 280. And you just write the genotypes to the right there, and that's your gene arrangement. It's pretty simple. For B, it asks for the gene order, and for that one, something that's helpful is to set up 3 different gene arrangements, with each allele being in the middle. And then you locate the 2 least greatest categories, which is the 10 and the 14, and you write those so you have something to look at there. And then you do a double cross to determine which one, when you cross it, is going to give you that genotype of the 2 least amount. And so we determined that would be the S, SC plus, and V over S plus, SC, and V plus. And then number C asks for a linkage map. And again, you just kind of add up the totals of the 2 least greatest, and then you do single crosses. So for, let's see, the 30 is the SC plus, the S, and the V plus. And then the 46 is the SC, S plus, and V. So you add those all together, divide them by 1,000, which gives you 10 map units, or gives you 0.01, and then you times that by 100, gives you 10 map units. So that's the distance between the SC and the V alleles. And then you do the same thing down for the S and the SC alleles, 24 plus 150 plus 156, and that gives you 33 map units. And then finally, to calculate your interference value, you take the original map units, which would be 0.33 times 0.01, and you times that by 1,000, gives you 33. Then you plug that into the interference equation, so that's 1 minus 24 over 33, which gives you 0.27 or 27%.
Perfect. For question number 3, we're asked to kind of do the same thing which we did with the other 2 problems. And so in part A, we're asked to determine the gene arrangement for the 3 linked genes. As my colleagues have said before, what we do is we find the most frequent gene or genotype, and we find that to be the 484 as well as the 441. And so we take the phenotypes of those and just kind of put them in or put them together, and so we get G plus, or the wild type of G, C, and the wild type of S, all over G, C plus, and S. And so that is our heterozygous parent. And so for part B, what we do is we take this heterozygous parent and we kind of shift things around. And so we'll have each of the alleles or the genotypes be in the center. And what we'll do with this is we'll actually take the least frequent genotype, which is 11 and the 8, and we'll get their phenotypes, and this is what we're looking for. And so we do this little crossing, and we find that the first option will give us the pattern as the least frequent alleles are produced. For part C, we can do the same thing. However, it's a little bit tricky because we notice that there's only 6 results that we received. However, with this, there's actually 8. But for some reason, there are no values with the other ones. And so we can use those as zeros just for as our kind of placeholders. And then we'll take the 27 and the 29, divide that by 1,000, times that by 100, and we'll get 5.6 map units. And this is between the C allele and the S allele. And then we do the same thing, but instead of putting 27 and 29, we use 8 and 11, and we get 1.9 map units for S and G. And so when we do the interference value, we times these together, we get this 0.00164, and then we times that by the total value, which is 1,000, so we get 1.064. But when we do the totals, we notice that we receive a negative value, and that negative value is negative 16.85. And what happens with this is, because there is a negative interference value, there technically isn't any interference at all, and so it'll just be 100% frequency. So,
okay. And then on to number 4, it's kind of just like all the other questions we've done, but it explains what the recessive genes are, and then it gives us the test cross information as shown. Okay, so then for part A, we determine the gene arrangement for these 3 linked genes. Okay, so that's pretty much just the same thing. We're looking for the parent arrangement, so we take the 2 highest numbers, 379 and 385, and find those phenotypes respectively, and we get what is shown right here. Okay, and then for part B, we determine the gene order for these 3 linked genes. We take the 2 smallest, which is 2 and 3, and find those phenotypes respectively. And then to find the gene order, we make down like copies, like we have those 3 different outcomes that are double crossed. We find which one makes it look most like the one we found in part B, and so that's going to be part C, or not part C, the third one of the 3. So that's the gene order there that we have shown. Okay, so then we go on to part C, and it's just calculating the map frequencies again. It's kind of just the same equation we've been using. So we go 2 plus 3 plus 26 plus 20, and then divide by 1,000, multiply it by 100, we get 5.1 mu. Same equation, just different numbers. 2 plus 3 plus 98 plus 87, divide by 1,000 times 100, and we get 19 mu. And those are between BR and F, and then the F and AN respectively. Okay, and so then to calculate the interference for part D, we take the 5.1 divided by 100 times the 19 divided by 100, and we get the 0.00969. We multiply that by the total number of offspring, and it gives us 9.69. So then we take the expected outcome, which would be 2 plus 3, or 5. We go 5 divided by the 9.69, subtract that from 1, and that'll give us our interference value of 0.484 or 48.4%. Okay, and then on to question 5. For part A, it says, suppose the cell has the genotype A, little a, B, little b, assuming that the A and B alleles are on separate homologous chromosomes, meaning that they're not linked. Then the B and B alleles, what are the genotypes of the gametes produced by this cell? What is the frequency of each of these gametes? So this is pretty much just what we've learned in past chapters. We're just going to run a basic Punnett square to find, as we show here in part A. We just get those 4 different outcomes for gametes, and we know that each one is equally opportunable, so each one is 25%.
So for part B, we notice that A is linked to B and little a is linked to little b. And so with this, or if the gametes were to be produced and if they were connected and there was no crosses between them, we would notice that there wouldn't be any crossing over, and so the frequency would be just big A, big B, and that'd be 50%, and little a, little b, and that'd be 50%. And so what will happen is a big A, little b, and the little a and big B will have 0%, just because there's no crossing over happening. With part C, we're asked or the question is, suppose the cell has the genotype heterozygous A, heterozygous B. Again, A is linked to B and A is linked to B. What are the genotypes and the gametes produced by the cell if crossing over occurs between the A alleles and the B alleles? And so what happens is we have a crossing over that happens right here between A and B. And so these are the phenotypes that can be produced.
All right, so D, it goes in more depth and asks you for the frequency of each of these gametes mentioned in part C. And so even though in part C those are possible, they don't all have the same chance of occurring. And so it gives you the map units, which is 7.8 between those two alleles, and that is actually also equal to the chance of recombination. There's a 7.8% chance of recombination. And so you take, so we know that the parental gametes are the ones with no crossovers. So that's going to be your homozygous dominant and homozygous recessive. So we're going to leave those alone for right now. We're going to focus on the heterozygous ones. And of those 4, that gives us a 50% chance, or not 50% chance of happening, but 50% of those 4 are heterozygous. And so you're going to take 50%, so 0.5, and you're going to multiply that by the 7.8 map units, or 7.8% chance of recombination, which you could say is 0.078, which gives you a 3.9% chance of happening. So that's your chance of recombination. So that's your chance of the heterozygous gametes being produced. And then for the parental gametes, you just take the remainder of the other 50%, and you subtract 3.9%, gives you 46.1% of those gametes happening.
Thank you for listening to us.
Good luck.